Oh, pause and copy. Please pause and copy. Pause and copy. Okay, pattern recognition, which we're going to be doing in part A here, is a bit of an art form. I would start by saying we have A1, A2, A3, A4, A5. Now I'm going to basically just guess a form for AN and then check. And I'm going to do one thing at a time. I'm going to look at just the numerator. The numerator is linear. So that's like a linear is what? mx plus b, or maybe ax plus b. So in our case, it's going to be something times n plus b. Now I'm going up by 1 each time, so it's going to be just n plus b. If we were going up by 2 each time, then I would put a 2 here. If we were going up by 3 each time, I would put a 3 here, but it's not so. It's going up by 1n each time. Now I want a1 to give 4 over whatever. So I think from this I deduce that the numerator of A1 has got to be n plus 3. And this way, A1 is going to be 1 plus 3, giving 4 on top. Okay, on the bottom, what do I notice? I notice that 8 times 2 is 16, times 2 is 32, times 2 is 64. So I'm multiplying by 2 each time. So maybe we want to start with 2, oh boy, that's not what I want. Oh, that's linear. Don't want that. So maybe on the bottom, I want to start by guessing 2 to the power of n. But then I would say, well, if I look at A1, I'm going to get just 2 on the bottom. But that's no good. I should be getting an 8. But I can fix that by saying I want A1 to give 2 cubed downstairs. So I can fix that by just adjusting. Put a plus 2 there. Okay, so it's a bit of an art form. It's a little bit not super precise. I start with a guess, and then I have to adjust sometimes. I should double check now. I should take my formula, and I should go say A4. What's it going to give me? It's going to give me 4 plus 3 all over 2 to the 6, which is 7 over 8 times 8, 64. Yeah, good. It does check out. All right, so now I can do the limit with this AN. So the limit is going to be a limit of this thing I found, n plus 3 all over 2 to the n plus 2. And I'm going to use L'Hopital's rule. So L'Hopital's rule allows us, if you have a function that kind of matches this, you know. So we'll say, let's look at limit as x goes to infinity. My original was n goes to infinity, but I'm going to switch to x so I can use L'Hopital's rule in derivatives. I'm going to look at x plus 3 all over 2 to the x plus 2. Now this is of the form infinity over infinity. So I can do L'Hopital's rule. And on top you get 1. On the bottom you get, let's think about this, 2 to the x plus 2. That's going to be 2 to the x times 2 squared, rather. So it's 4 times 2 to the x. So if I do a derivative here, what do I get? I get 4 times 2 to the x times ln 2. In any case, what I have is a 1 over, now the denominator is still going to infinity. So this is going to be 0. Okay, so the limit of this fraction here as a function is 0. So I can conclude that my original an also has a limit of 0. Okay, so the idea here is that if you have a function that matches your sequence, and as long as it's a differentiable function, top and bottom differentiable, there's a few other conditions we won't dwell on, but under most situations that we'll see, this is a fair tactic. Use L'Hopital's rule and make your conclusion.